So, the measure of the amount of disorder in a system is called entropy. If disorder increases, then entropy increases. Entropy can decrease if work is put into the system. Living organisms take in food or extract energy from the surroundings and become more organized. So, your locker gets messier each week. In this case, the entropy of your locker would be doing what? Increasing. Because if your locker were to become more organized each week, then the entropy would decrease in proportion to the effort expended. So in order to decrease entropy, you have to extract energy from the surroundings and put work into it. Eventually, you'll run out of energy and you'll stop being able to maintaining your locker, and without putting energy into it, your locker would over time become more disorganized. So the net entropy of the universe is continually increasing. It's continually running downhill, as the expression says. We say say net because there are some regions of energy in which it's actually being organized and concentrated. So again, this is statistical. If we look at the system as a whole, overall, the system is becoming more disorganized. Galaxies are spreading out, stars are expanding and exploding, they're sending their guts everywhere, everything is becoming more disorganized. There are some regions where the opposite is true. There are some areas where we have clouds that are constantly concentrating their energy due to gravity. But overall, we have a net effect where its entropy is increasing. So in living organisms, they survive by concentrating and organizing energy from food. And energy must be transformed in the living system to support life. When it isn't, the organism soon dies and tends toward disorder. So humans are an example of a system where we concentrate energy from food into higher, more easily usable energies. But if you look at it as a whole, the amount of work we put in to get all that is eventually going down. So all life on Earth is eventually supported by the sun. The plants absorb energy from the sun. The sun is constantly losing energy. It'll eventually run out after millions and millions of probably like a billion years or something. It'll eventually run out. And then once that source of concentrated energy runs out, disorder will continue and resume. Overall, the net effect is the solar system's energy is indeed going toward disorder. All the energy from the sun is spreading out. But if we zoom in and just look at a small section, such as an organism, they're concentrating energy. But if we look at the system as a whole, it is going to disorder. So there's a very famous expression and meme in physics. Every action that you do contributes to the heat death of the universe. If we were to continue playing out the laws of physics out in the universe and look far, far into the future, as this order continues to increase, we'll eventually run out of useful work. All the matter and all the energy of the universe will spread out. There will be no temperature gradients, and we saw that in order to actually have an engine or do any useful things, we need a temperature gradient. In order to actually do useful work, we have to have two things at different temperatures. Eventually, everything will reach the same temperature in the universe. This is billion. I can't even say how many billions this is. This is like 10 to the 40 years, which is like 30, 20 orders of magnitude. Actually, they estimate, it depends on whether or not a proton can decay. It could be 10 to the 100, which is a number so large there's not enough atoms in the universe. If we let every atom or every proton be a zero, and we lined up all these zeros, there's not enough protons in the universe to write that number out. That's how long it'll take. But the idea in physics, if we look at into the future, we're pretty sure the universe is going to end by heat death. We're going to assume that looking at it, as stars react by fusion and fission, they keep making heavier and heavier elements. Nickel and iron are the most stable. Eventually, all the atoms in the universe will turn into iron, and you can't do any nuclear reactions with iron. Oh, so we'll eventually get iron suns and black holes, and everything's going to equal the same temperature. Occasionally, we'll get occasional sparks where two iron stars will collide, have some fusion going on as the impact breaks the iron apart. But overall, it's going to end up in heat death. And there's always a joke that doing your homework is a protest. You should not do your homework because doing it increases the rate at which the heat death will occur. So the second law of thermodynamics is probabilistic statement. Given enough time, even the most improbable states may occur. Entropy may sometimes decrease. For example, the haphazard motion of air molecules could momentarily become homogeneous in a corner of a room. So statistically, all the air in this room could just randomly bounce and move toward one corner, and that would be a decrease in entropy. These situations are possible, but they are very improbable. So let's look at the laws. This PowerPoint didn't have one law. So we have the 0th law. Zeroth law of thermodynamics. If we have a container A, and we put it next to a container C, and we notice no flow of heat, and then we take a container B, and we put it next to container C, and we notice no flow of heat. Then the 0th law of thermodynamics states that container A and container B are at the same temperature. Which makes sense. Heat always flows from hot to cold. If A and C have no flow of heat, that means they're at the same temperature. If B and C have no flow in heat, that means that, so the temperature of A has to equal the temperature of C. And if B and C have no flow of heat, then they're at the same temperature. So the temperature of B has to equal the temperature of C. And by using very simple math, if A equals C and C equals B, then A has to equal B. Which makes perfect sense. Nothing, any trickery going on there. The main statement of the 0th law of thermodynamics, another way of stating it, is objects of the same temperature are in thermal equilibrium. What this basically means is if two objects are at same temperature, the net flow of heat is 0. Because now statistically, if the molecules that come over here and hit this one warm B up and A gets colder, then statistically the heat is going to flow from hot to cold until they reach the same temperature. So even if there is some temporary flow of heat, it'll quickly normalize and reset itself so that they're at the same temperature. What this law allows us to do is assume that basically we can assume if two objects are on the same temperature, the net flow is 0. We can just make that assumption. The first law of thermodynamics basically states that the change in energy is equal to the heat put in minus the heat done by. I really hate this equation because in chemistry we put the plus sign here and define work differently. We just change the sign, we change the definition. But this is also a restatement of energy can neither be created or destroyed. Basically, it's conservation of energy. The second law states that heat itself never spontaneously flows from cold to hot. From a cold object to a hot object. If it does flow, it only flows hot to cold. Another wording of this is order tends to disorder. Things that have a high amount of order, they tend to go to disorder. So, let's apply some of these examples. Let's say I have some water and I put some salt into it. What is going to happen? It'll do what? It'll dissolve. So right here we have a high concentration of salt molecules. The salt forms a crystal lattice. So we have this very organized structure where all the molecules are all bonded in a very particular way. We have this very organized system. And when we put it in water, the second law tells us that the NaCl molecules are going to want to spread out. That eventually we're going to have random, the crystal structure is going to go to, so the crystal structure is highly organized. And when we put it in water, the crystal structure is going to break down and spread out throughout the water. If you put dye into water, you're going to have it, food coloring into water, you're going to have it spread out. It's going to become more disorganized. So let's do some, if you add 500 joules of heat to a system and do 250 joules of work on the system, what is the change of energy? What is delta U? So change of U is equal to Q minus work. So Q, well, here's our system. Q is when it's added to the system, and work is when it's done by the system. So it says we're applying it to the system, so Q is going to be positive. So we put in a positive 500 joules here. And we're doing work on the system. So that's opposite to what it was defined. So we put in a negative 250 joules here. So we get 750 joules. So you have to remember directions. In chemistry, which I don't teach this equation in chemistry, they do it like this. To where heat is onto and work is onto. In physics, since we usually deal with pistons, it works out oftentimes both of these values are positive. And that's the reason why we changed the definition in physics, which I very dislike. So you need to know most definitely the direction. What is adiabatic? Yeah, no heat leaves our enter system. So let's do an example. Let's suppose I have a cylinder. And let's say I heat it up. I'm going to add a fire to it. And it's going to very slowly expand so that there is no change in temperature. So pressure is increasing. And then I'm going to remove the fire. I'm going to let it very slowly reduce back down. So that there is, again, no change in temperature. And then I'm going to add the heat source again. What type of system is this? So here is fire, and fire is adding heat to the system.
This is isothermal.
Isothermal. So remember, there's a difference between heat and temperature. So even though the heat, or I should say, even though the temperature isn't changing throughout this, we are having fire add heat overall. It's just allowed to expand so that that heat energy is dissipated throughout it. So it's not adiabatic because we have an external source of energy that's being added to it. And while we let it very slowly cool off, heat is radiating outward. Trying to figure out some more things I could say. All right. Let's suppose we have a balloon. So a weather balloon. It has some volume. And we let it go, and it gets up to a very high altitude. And it expands because of low pressure. What process is this? So it has some volume, and it expands at some height, to some bigger volume. So volume is increasing. So the pressure on the ground is higher than it is up in the air. So pressure is decreasing while volume is increasing.
It's like
isochoric is the last one. That's constant volume. The volume change. I hope the volume changed. It just said it got bigger. So it's not isochoric. It's not isobaric. Which means you have two other choices. Isothermal or adiabatic. So if you increase the volume and decrease the pressure, what happens to temperature? Well, as you decrease pressure, decreasing pressure is the most major change. So temperature is going to go down. Also, it's colder up there. It's adiabatic. There is no transfer of heat. The work done only depends on the pressure and volume changes. This process right here, I haven't mentioned it, is something called cyclical. It means it repeats on cycles. On the test, I'll give you a hint. None of them are this because I don't teach it. Oh, I also forgot this. Isochoric. I can't believe I forgot this. Another name for this is isovolumetric. These are the same thing. So this, technically, the full name of this would be this. This is isothermal cyclical, meaning it repeats in cycles. So let's suppose that we have a flat on a bicycle wheel, but you have a CO2 canister, like for a paintball gun. So you take your CO2 canister, you hook it up to your tire, and it instantly inflates your tire, but does it so quickly there's frost on the canister. It freezes. What would this be?
Is the pressure increasing?
Yeah, so the pressure inside here is decreasing, while the pressure inside the tire is increasing. So it's not isobaric. So the temperature here is going down. The temperature here is, so as the gas, so as volume, as volume increases, what does temperature do? It should increase, but it doesn't in this case. Because as gas expands, the temperature is going to fall off. That's because of pressure. Again, the pressure is changing too. This assumes constant pressure. But if you have a situation where the volume is increasing and the pressure is significantly going down, then the temperature is going to go down because pressure is more important. So this is a case where all three apply. As the gas, so the volume is increasing, but the pressure is I'm trying to think, because inside the tire, when you add the gas, it's not expanding, it's compressing. I don't know about temperature. My intuition tells me it decreases, but that violates the law, so it has to be wrong. But we can rule out isothermal. And we can rule out isochoric. Is there an exchange in energy between the two systems? So here is another thing about adiabatic I forgot to teach. Adiabatic is reversible. I believe that's correct. This is a situation I'm reading this problem is called free expansion, which I haven't taught. It's not on the test. I just wanted to cover this example, as it's a situation where none of them apply. So there is going to be heat transfer because frost appeared. That means that we're absorbing heat. If when we see frost appear here, it means that this has to be absorbing heat. So when you have a liquid, and we pull all the heat out of it, it'll turn into ice. Likewise, if this gas pulls all the heat inside of it, then the outside container turns into ice or frost. That's the reason why this isn't adiabatic, is because we saw frost formed. Because frost is formed, that means it's pulled the heat from the air inside of it, so temperature would be increasing. Because it's pulling heat inside here, making the air inside here hotter, making this colder because of that pull. It has to be getting heat from somewhere. Alright, let's see how your entropy is. So let's say I have a glass of water at 60 degrees Fahrenheit, and I have the same glass of water that is at 80 degrees Fahrenheit. Which has more entropy? Why? What is entropy? How disordered something is. Another way of thinking about entropy is how random something is. If you were to place books in alphabetical order, so A, B, C, D, E, and so on. Now let's say I took these same books and threw them out into the world, onto the floor. They'd be very disorganized, right? They'd basically be random pile. You can't extract any information from a random collection of books. Whereas if I ask you what letters do I have in this collection, you can easily see how many letters. This is highly organized. If I asked you to go look at a random collection of books on the ground, you'd have to pick them up one by one to look at it. So as we increase temperature, remember that temperature is average kinetic energy. If we're at a higher temperature, that means we can have way more variations in kinetic energies per particle. Versus here, all of them basically have to be about the same. We have less range, so this has higher entropy. So, for example, going back up to, let's say we're heating some salt water. So we have some water, and we're putting in a cube of salt or sugar. This is where it has the most or least entropy. The moment this touches the water, it's still crystal. This is where the entropy starts going down. Then as the sugar breaks apart and becomes partially dissolved, then when we have it fully dissolved throughout it, and then lastly when it increases temperature. So why doesn't a broken piece of glass reassemble itself and jump back on the table all completed? What law does that violate?
First law.
Energy is conserved when it falls off the table. All that energy is still there. This is the second law. The second law says order tends to disorder. We're going from a system that has a lot of randomness, so a lot of disorder, and we're going to a very to a high order. So this is very randomly distributed, the glass pieces, and we're restructuring the crystal structure to complete the glass. So this is a violation of the second law of thermodynamics. So let's say we have a wheel with some magnets on it. And around this, we have a very, very strong magnet with a north pole, so it pushes these magnets and make it spin around in a circle, getting faster and faster and faster. Is this possible? And if not, what law does it violate? Hmm?
You can like have a magnet on the table and then have one spring on top of it.
This is a perpetual motion machine. So imagine I hook this up to a generator. Could I just put a magnet next to my generator and produce infinite number of electricity? That should immediately tell you this is not possible. This is called perpetual motion machine. They do not exist because they violate the laws of thermodynamics. So we're putting in here, we're putting in 0 work, and we're getting out of it energy. And if we remember the ideal efficiency of an engine is less than 100%. There is no 100% efficient engine. So this would be a violation of, I should have added this too. This is a violation of the second law of thermodynamics. The second law states that the ideal efficiency of anything cannot be 100%. So this is applied to heat engines. So one way of thinking about this is as this is running, it's going to be generating some heat. So we have this cold to begin with, and all of a sudden it starts gaining a lot of heat. So that means that heat has to be flowing from cold to hot. This is a violation of the second law of thermodynamics. Another thing you can add to the second law is no 100% efficient machine. It comes from the statement that things never go from cold to hot spontaneously. You should recognize that we can't have free energy. This does not work. What happens is, even though this is pushing on this, it's also pushing in that direction too. There's no way to configure magnets so that they don't push on each other and stop. Let me see if I can. We'll review some more tomorrow, but let's see if I can. Perpetual motion machines.
Writing's not that easy, but grammar.
Yeah, the bell's going to ring before I can. So this video is fake. All of these are fake. Even though the title of the YouTube video says all of these work. So we have a heavy object. Because of gravity makes it constantly spin. That doesn't work. Friction will slow it down. This is rolling. Wrong. Off-centered weight. Again, none of these situations work. We can't build a perpetual motion machine. Tomorrow I'll review. I broke this test up into 2 sections. We'll review. This is going to be the review, but I ran out of time. We'll review more tomorrow on it.